Okay, recording initiated. There it is. Today's topic is definite integrals using our programs and by hand. Also, we're going to practice a little bit with MTSC, midsum and trap sum and Simpson's rule. We talked about average value prior. I don't know if I'm going to talk about that too much. And today is the 10th. Let me get a program. What's my program got here? We got MTSC, 2 M's and a T, right? Okay. All right, so let's do one of these MTSC programs by hand and then see how the program works. I gave you the program, you're going to enter it later, okay? You don't have to worry about entering it now. So, if I want, yeah?
Is that L or 1?
L for left sum.
Oh.
Just like the original program. You'll note if you're entering MTSC, it's almost the same as LRTE, a couple of additions to get an M and an S out of it, that's all. So here's an example. Let's say I want the area from, 0 to 4 under the curve e to the negative x squared. Now this you have to use a program. Some kind of a program. Or if you're using the calculator, where'd the calculator go? It would be second 7, right? You can use second 7, which is basically a program to do Simpson's rule built into your calculator. Okay? But let's use our program. Why? Well, because you can't do an antiderivative, an exact closed form algebraic antiderivative. There's no like U sub you could do here. And we talked about U sub a little bit. This you can't do it algebraically, you just can't. So we're going to do it by hand. We're going to draw some rectangles and stuff. We're going to play around with this. Okay? So, how about we do a midsum, which we haven't had a chance to do? Okay. Now, e to the negative x, what does it look like? Well, let's see. Let's just graph that. All right, turn HAL on, go into y equals, take e to the, which is, it's diamond x, right? And it's a negative x squared, so negative x squared. Enter. Where's my enter? There it is. And then how about a zoom 4, just make sure. Whoops, zoom 4. Well, I think I'm in zoom 4 already. And there it is. So it's that bell-shaped curve from statistics. You ever do bell curves? Right, that kind of standard deviation, right? It's based on this. It isn't this, but it's based on this. I think the z chart is based on a function like, yeah. You know the z chart, right? It's based on a function e to the negative x over 2 quantity squared divided by rad 2 pi or something. It's some crazy thing. It's a normalized curve such that the area under the curve is 1 or 100%, right? The whole population. Anyway, but that's statistics. I didn't say that. It's top secret. So it looks like that. Here we go. So let's say this is 1, right? If you plug in 0, e to the 0 is 1. And it goes asymptotically to the x-axis. So it looks something like that. And let's say this is 0, 0, 1, 2, 3, and 4. Okay? Now, how do I do a midsum with, say, 2 equal rectangles? What do I mean by equal rectangles? Delta x is the same, right? Equally spaced. So what's your delta x? I want 2 rectangles. What's your delta x? 2, okay. So we're going to go for a base of 0 to 2 and another base from 2 to 4, right? So we have a rectangle that has a height here and has a height here. But how high does it go if I'm doing a midsum? Do you guys know how to do this? Right, we want the height at 1, as it turns out. Okay? So it's going to look something like, well, I should get a rectangle. Give me a rectangle. Something like, I don't know. Such that we hit the height there, say, right? This is the height, f of 1. All right, so that's a midsum. And what's the next height going to be at? F of who? F of 3. Okay, good. So let's draw that rectangle. Something like that. So the F of 3 is the height. Okay? So it's very simple to figure out this area, but it's not obvious whether it's an overestimate or underestimate, is it? I know we said last time that trap is an overestimate when you concave up. As it turns out, mid is an underestimate. An underestimate when you concave up. But this function changes from concave down to concave up. So I really don't know what the error term is going to look like at all. I don't know if it's an overestimate or underestimate. I really can't tell until I do the table. I'm going to do the table in a minute. But can we do this by hand? What's the area? It's going to be approximately what? It's going to be delta x, which was how much? 2, times f of 1 plus f of 3. Whoops. Okay? Oh, let's write it more in general. F delta x. Now we know delta x is 2. So we're going to say 2 times what? Well, e to the negative 1 squared plus e to the negative 2 squared. I'm sorry, 3 squared, sorry. Ding. Put a little 9 here. And this, I don't know exactly what it is. I could calculate it on the calculator, so let's find out what that is. So what's 2 times e, 1 over e and 1 over e to the 9th? Basically, that's what we're saying. Okay, so let's turn that on. And let's go home. And let's clear out stuff. Okay, so I want 2 times e to the negative 1 plus e to the negative 9. All right, now that's going to give me the exact answer. Oh no, I'm in approx. Okay, that's what I want. So this is rounding off the nearest 4 places. I usually state my answers to 3. So 736. Is that about right? Okay. Now let's do this with the program and see that it agrees. Okay. I'm going to do this with a convergence table where n is first 2, like here, 2 rectangles, then 4, then 8, then 16, like that, and see if we get a little convergence. You'll find that you don't need such humongous n's like we did last week with LRTE. Simpson's rule converges very fast. Once it starts converging, it's really, really fast. Okay, so hopefully this will work out to our favor. Here we go. Let's do an MTSC table. Okay, so a little table here. Okay, I need a column for N, a column for M, a column for T, a column for S, and a column for the error. Okay? So N, how many rectangles? M, the midsum estimate. T, the trap sum estimate. S, the Simpson's estimate. And the error term for Simpson's rule. Okay? Which is all in the program. What? This is M, midsum. Yeah, that's not much better, but there it is. And we'll start with 2, and then we'll do 4, and then we'll do 8, and then we'll do 16. And who knows, I might not even need more than that. It may already be convergent in fix 4. Okay? So let's run the program. Now, you don't have the program yet necessarily. That's okay. But I have it here. So the one that I gave you on the sheet. So let's run it. Now, first thing to remember is that y1 has to be the function, right? Then I did that already. Second thing is, let's run the program. From second varlink. Okay, second varlink. Did you get the sheet? No. Okay, yeah, you can enter this in later. We did this last week. This tonight you're doing. I'm using it now. Okay. All right, now, if I go, let's see. Let me close this. Where is my Area 2 folder? I thought I had an Area 2 folder. Well, that's okay. I have an Area folder, so Area has this program in it, so there it is. So here's LRTE with the while statement, I think. Okay, I want MTSC. There it is. I'm going to show you how it works. Once you get it working, you can test it. Okay, what I do, what's weird? I'm not in the right folder. Whoops. Yeah, that's not going to work too good. So change it, go to mode, make sure you're in the right folder. You probably still are, right? Yeah. Somehow I didn't save my state from last time, which is bad. Okay, so varlink, and let's do MTSC. All right, that should work better. All right, so let's say, well, what is A? 0. And what was B? 4. And how many rectangles did I want to start with? 2. And MTSC gives you M is 0.736. Isn't that what we just said? We did it by hand, right? Trap is 1.036 something. And Simpson's rule is MTS, 0.836. Okay. Well, it seems to be an overestimate. Now remember, the error term doesn't mean anything unless it's less than 1, but let's write this stuff down. Okay, it's 0.736. Okay, let's write it all down. .736. I'm doing a fixed 4 convergence table, right? I lost it already. 10366, okay. And where'd it go? .8362. And the error was exactly 1, apparently, at least in 4 places. Okay, now what I'm going to do is I'm going to run it for 4. But look what it's doing. It's waiting for me to enter another n. So you don't have to hit F5, get out of the program's output screen. You don't have to var link, start the program all over again. You don't have to enter A and B again. Just enter n. The program is still running for the same A, the same B, the same Y1. Okay? So n is 4. What are you doing? Give me Cal. Okay, so n is 4, and let's see what we get now. Okay, so it's .8861, .8863, .8862, and .2500. All right, so they're all 88 something, 61, 63, 62. I should be consistent. I should have either nope, don't put the 0 in front, or put the 0 in front. Well, let's do it like this. All right. So .8863, .8862, and .2500. Now the error term is less than 1. What is it telling me? What place has no error? The ones place has 0 error. If you write the 0 there, it's obvious. Okay, and is there round-off error? If this is 5 or more, this is not necessarily the case, right? Is this 5 or more? So we have 0 error in the whole number place, but wow, thanks a lot. That's 0, thanks. Wow, I didn't get much of an answer, did I? The area isn't 0, is it? So that's not very helpful. All right. But wait, there's more rectangles. Let's do it for 8. Notice I'm not doing huge numbers here. 5, what did we do last time? 5, 25, 125, 625, 31, 25. I don't need humongous numbers. You'll see why in a minute. All right, so let's run it for 8. Look, it's waiting patiently for us to plug in n. And look, it looks like they're all the same. That's interesting. So .886, what was it, 2, right? .8862, .8862, and the error term was 0625. 062, whoops, .0. 625. Okay. Look what's nice about this. This is Simpson's error. Once Simpson starts to converge, if the error term is less than 1, we'll say that it's converging. Once it starts to converge, the error term gets smaller and smaller really fast. Notice the square of 1/4 is 1/16. The error terms get smaller and smaller and smaller by the square, since I'm doing powers of 2. Which is nice. If you have a number less than 1 and you keep on squaring it, what's going to happen? Get smaller and smaller and smaller. That's what you want. You want the error term to go to 0. Now, as far as the Simpsons column is concerned, do we have convergence? We had it here. We could have stopped right here. Without looking at this, we could have stopped right here. Simpsons is the best, the quickest convergence. It's better than even trap. Last time we said trap will make you stop sometimes. Here it's Simpsons. It will make you stop sometimes. Why is it so good? Because it's like a trapezoid, but the top isn't a line segment. The top is a parabola. So it matches the curvature a little bit better. Whether the function is concave up or concave down, increasing, decreasing, it matches that a little bit better than just a line segment. Okay, so this is going to converge really, really fast. Notice, even for very small n, look how nice it is. If the function was in fact a parabola, we would have had the exact answer the first time out. As it turns out, that was a fluke. That doesn't usually happen if it's not a parabola. Notice we... What's that? Oh, was it really? What was it, 0.8333? 3, 6, yeah, that's what I wrote. What do you mean? Oh, they're not the same. Oh, okay. I'm thinking this is the same. They're not the same. Oh, you're right. Okay, good. They're not the same because it's an egg 3. Duh. Okay, but they're the same here. Okay. But like I said, if you had a function that was parabolic to start with, okay, you'll find that you'll converge right away because the parabola at the top of the Simpsons rectangle will match exactly the first time out. Okay? Now, we're not actually calculating areas on the parabolas. What we're doing is we're taking the weighted average of two midsums and one trap sum. You know how to do a weighted average? What's a weighted average? Where some term weighs more than another term? If I have two mids and one trap, I'm averaging how many numbers? If I'm averaging two mids and one trap, how many numbers am I averaging? 3. So I'm going to take 2 of these plus 1 of these divided by 3. This one counts more. As it turns out, just like the average of L and R was trap, the weighted average of 2 mids and 1 trap is Simpson's rule. Whoops. Okay? So why don't we do a trap and see that we get this answer? All right, because we can do this by hand. We know how to do a trap by hand. We just did the mid by hand. And then if we get these two answers, we'll take the weighted average of 2 of these plus 1 of these over 3 should give you this. You can do this all by hand. You don't need a program. Okay? You probably need a calculator to get powers of E, but that's about it. All right, so let's try that. Let's go back to where we was. Where was we? Yeah. Where did my page go? My page went away. Where did it go? Oh, there it is. Okay. Ta-da! Okay, so what do I want to do? I want to do the same problem, but now with a trap, which is easy, right? We've done trap. Let's redo the same question, get the area for trap, and then we'll do the weighted average of 2 mids, right? This is mid, okay? 2 mids and a trap, and see that we don't get Simpsons, okay? So pretend you have a trapezoid with a parabola on top. Pretend you have a trapezoid with a parabola on top. That's what we're trying to emulate with Simpson's rule. Okay, let's graph this again. So let's do a trapezoid picture here. All right, so this is 1, and e to the negative x squared looks like that. And again, I'm going to break this up. 1, 2, 3, 4. Now, how are you going to do 2 equally spaced trapezoidal rules, or trapezoidal rectangles? Well, I'll draw a height here. That's not what I wanted. I wanted this. Okay. I'll draw a height here, and then and the height here, and then what? How do you draw the trapezoids? You connect this endpoint with that endpoint, right? And connect this endpoint with this endpoint. Notice how trap is underestimating here when it's concave down, and overestimating here where it's concave up roughly. Mostly concave up. May not be concave up for all x, but close enough, okay? So I'm trying to get the area of this trapezoid and the area of this trapezoid, okay? So to estimate this area with a trapezoid, how do you do it? Well, delta x is still 2, okay? And that's the height of the trapezoid. Remember the bases? We take the average of the 2 bases. So base 1 is f of 0, base 2 is f of 2, right? F of 0 plus f of 2. Don't forget, we're taking the average of this. I'm going to pull that outside. Divide by 2. Plus base 1 here and base 2 here. So that's another f of 2 plus an f of 4. That's what we got to do. Okay? And again, delta x is 2 in this example, so this whole thing is 1. So I just have to figure out f of 0 plus 2 f of 2's plus 1 f of 4. That's all I got to do for this trap problem. And that's going to be e to the negative 0 squared is 1, plus 2 times e to the 2 squared is e to the negative 2 squared is e to the negative 4, plus e to the negative 4 squared is e to the negative 16. That's the exact answer. For my approximation, that's silly, but there you go. What's that as a decimal? I don't know, let's see. Let's ask Hal. Okay, Hal, do some work with me, will you? Because we're just going to calculate this thing, just give it an idea of what decimal it is. By the way, how do I stop this program? N equals 0 will stop the while loop. Then you can have 5 out. Okay? 0 rectangles, that's not a problem, it stops. Okay, so what is this as a decimal? Just curious. 1 plus 2 times e to the, what is it, negative 4? and I'm in approximate mode, so it'll give me a decimal, plus e to the negative 16. And you got 1.0366. Does that sound familiar at all? Yes, we got that already somewhere. 1.0366. Isn't that what we got for trap with two rectangles? There it is. This is exactly what we're doing. All right, now I want to take two of these plus one of these and average them over 3, and I should get that, right? But I don't want to use this answer because it's rounded off. I don't want to use this answer because it's rounded off to get this answer, which I'll round off when I'm done. I'm going to use the exact value, right? Now, what's the exact value? There it is. So I need two of these and one of these. And then I'm going to average them out. So this is trap, okay? I might as well put it down here. Hello. This is the approximation for trap, right? Now, what is Simpson's rule? Simpson's rule is 2 mids plus a trap over 3, okay? Now, how am I going to get 2 mids and a trap? I'm going to have to use the exact values because I don't want to round off 3 times, right? Now, I have these exact values in the calculator. That's mid for 2 rectangles. That's trap for 2 rectangles, right? Okay, so how about if I take this and store it as, I don't know, alpha m. Where's m? There it is. And then I'm going to take this and store it as t. And then I'm going to take the quantity 2 times alpha m. Where did my m go? Plus 1t divided by what? 3 is going to be my estimate for Simpson's rule. And it's 0.8362. Isn't that what we got? 0.8362, there it is. Okay? So, remember, the hard way to do this is to actually do some geometry and figure out how to make parabolas fit under here, and then get the area of all of that stuff without doing calculus, without doing just geometry. That's a bear of a problem. I'm not asking you to do that. I'm asking you to do, can you do a mid by hand? Sure. Can you do a trap by hand? Sure. You can do left and right if you wanted to also, right? And then can you take those answers and do a weighted average? Okay, sure. So now I've got approximately 0.0, what the hell was it? I forgot already. What the hell was it? 8362. That's only for 2 rectangles, right? We only did it by hand for 2 rectangles. 8362. Okay? Well, yeah. These are all approximations anyway. S is this. I'm approximating it with that. Okay? So there's where the dot goes. So that's how that works. Any questions on definite integrals using LRTE or MTSC? All right, you just got to type that thing in, and you're in business. All right, so let me ask you some other questions like that. Let's say, all right, what if I wanted this definite integral? Negative 2 to 2 under the area under the curve y equals square root of 4 minus x squared. Now this is another example where there's no closed form algebraic antiderivative that you could use. There's no function I could name whose derivative is that I know offhand. Not yet anyway. All right, if there is one, it's very difficult to get. We don't know how to do it yet. So you have another option. You can use MTSC if you want, right? But there's another option still. Do you not recognize this function? This is a typical part 1 question on the AP without a calculator. Yeah. That's just a semicircle, right? Sure. Okay. So let's see. If I want the area of a circle, in other words, isn't this what I'm saying? Y is 4 minus x squared, rad 4 minus x squared, right? What if I square both sides? Y squared is 4 minus x squared. What if I add x squared to both sides? Okay? So I'm talking about the area under this curve from negative 2 to 2. But remember, this is in function mode, right? This has to be a function. So I'm talking about the top half of this circle. So if I graph that, Let's see if we can graph that. Well, wait, let me get the circle in place first. Here's my circle, and here's my axes. I guess I'll do it this way. Maybe not. I'll start in the middle. Okay? So there's the origin right there. There's the x-axis, there's the y-axis. And then what is this x-intercept? Where does it hit the x-axis? At 2, right? Because this is r squared, so that's 2. So why did they say from -2 to 2? Because they're talking about this whole area bounded by the top half of the circle. Remember, this has to be a function. It has to be a continuous differentiable function, right? That we're integrating? Or the antiderivative, or the definite integral, the area may not exist. So we're only talking about this top half here. Well, what's the area of a whole circle? Pi r squared. So what I want to do is pi r squared, but that's the whole circle. What, am I getting the whole circle from this? No, I'm just getting the top half. So it's pi r squared over 2, and who's r? 2, and who's 2 squared? 4 over 2 is... You don't need a program for this. You don't need an antiderivative for this, and you're getting an exact answer. Usually you cannot get an exact answer without an antiderivative, right? If you're using a program, you get decimal approximations. That's all you get. Okay, so there you go. So sometimes, you got to use your wits, okay? And big hint, if this is on the no calculator section, there must be some way to do it without a calculator. What if, we got what, like 1 minute? I'm going to ask you a really tough question. You ready? Because everyone forgets about this. What's the area from 1 to 4 under y equals 5? Do you need a program for this? Do you need an antiderivative for this? No. Why? What's the shape of y equals 5? The yellow lines are straight, thanks. What's the shape of y equals 5? Horizontal line. Well, if you have a horizontal line at y equals 5 and you're taking delta x from 1 to 4, what's the area? 15. Do you really need a program for this? Do you really need an antiderivative for this? Okay, fine. What's the antiderivative? 5x, evaluated from 1 to 4. So that's going to be 4 times 5 is 20, minus 1 times 5 is 5. Okay, fine. Do you really have to do all of that? No. Use your wits. Sometimes you don't need to do all of that stuff. Okay. How about this one? What's the area from -1 to 2 of x sine x dx? Now, if it was sine x squared, this would be a u sub. This ain't. And this is not a function that you necessarily recognize the shape, like it's a circle, okay, pi r squared, right? There's no way to deal with this except what? Some kind of numerical approximation, some kind of numerical method, like our program or second 7, which is a Simpson's rule. By the way, second 7, if you're trying to find a definite integral with second 7, it's doing Simpson's rule with 20,000 rectangles built in. It's doing it at the chip level, so even though it's running 20,000 rectangles, it goes really fast. Okay, so it's basically, it may not be exactly Simpson's rule, but damn close, something like Simpson's rule, okay? So that's what you're doing when you do a second 7. So how do we deal with this? We'd have to do a convergence table using MTSC, right? Okay, so do so. Well, were we out of time? What's with that clock? Is that right? I know the hour hand is wrong. I thought the minute hand was okay. And the minute hand should be at 19. We got like 2 minutes, right? Well, you know what? I better stop my recording here because otherwise I'm going to screw next period. So, all right, we stopping the recording?